Ini maunya gimana? Boleh diserah ditanya atau satu-satu saja? Lebih enak.
Satu-satu saja.
Bisa saja. Oke, silakan Juli.
Assalamualaikum warahmatullahi wabarakatuh. Terima kasih Bapak Ibu yang telah menyempatkan waktunya untuk hadir di seminar pagi ini dan juga untuk alumni dan mahasiswa. Seperti yang sudah diintroduce oleh Pak Gedung, nama saya Biofisika Nuklir atau disebut lebih sering dipanggil Putri. Saya adalah alumni Fisika ITB yang dulunya dibimbing oleh Pak Gedung. Dan saya juga baru lulus S3 di The University of Tokyo atau yang lebih dikenal sebagai Todai. Sebuah kehormatan untuk saya untuk bisa hadir di sini dan menyampaikan sedikit riset tentang discrete element model dan beberapa pekerjaan selama S3 saya. Jadi seperti yang ditunjukkan di logo ini, Sakai Lab, saya S3 di Sakai Lab yang secara umum melakukan penelitian di bidang granular, terutama menggunakan discrete model, dan penelitian saya spesifik untuk non-spherical particle, sehingga judul presentasi saya adalah Discrete Element Modeling of Large Scale Systems Incorporating Non-Spherical Particles. Dan untuk presentasi ini saya memohon izin menggunakan bahasa Inggris di beberapa bagian karena ada beberapa istilah yang mungkin akan sulit diterjemahkan ke dalam bahasa Indonesia, sehingga untuk konsistensi saya akan menggunakan bahasa Inggris. Tapi dalam tanya jawab saya akan berusaha untuk menghandle dalam bahasa Indonesia. Jadi sebelum mulai presentasinya, saya sedikit perkenalan lebih jauh. Jadi saya masuk ITB tahun 2010 di Fisika ITB di bawah bimbingan Pak Dudung dan Pak Miftah. Kemudian saya melanjutkan S2 tahun 2016 di Fisika ITB. Getting an education in Japan was not my original plan actually, but Pak Dudung was so supportive and he successfully convinced me to study in a more advanced level. So I decided to study in the University of Tokyo to take another master's program in nuclear engineering and management under Professor Sakai's supervision. And then I entered the doctoral program in 2022 and just finished this year, 2025, in the same laboratory. So Professor Sakai is an expert in discrete element model, and his lab is recognized as one of the world's leading in granular simulation, and so it influenced me a lot, so that my research field currently is discrete element method or DM in granular simulation. So during my master's and PhD programs, I received several awards, but I especially thankful for being selected for lulusan terbaik Magister Fisika ITB in 2018, and 2 years later the Best Student Award from the Graduate School of Engineering, University of Tokyo, and while the others are awards from international conferences in Japan, Indonesia, and Germany. And now I'm going to start my presentation with the importance of granular and discrete element method in industries. So the granular is very common in both daily lives and in industries. Especially in industries, it is regarded as the second most used material after water, and it involved in almost every stage of manufacturing processes, such as raw material during the processing, or even as the final product itself. So understanding the dynamics is essential, is very important to maintain the output quality. And with numerical simulations, the numerical simulation can give benefits in many ways, such as design process specification, virtually troubleshoot problem, and even test and validate outputs even before they exist in the real world. To conduct the numerical simulation, the discrete element method is recognized as the most widely used method to simulate granular dynamics and gain insight into the behavior of particles in large-scale industrial systems. The key feature involved the overall behavior of granular material emerged from the interaction between individual particles, where this particle is calculated using physical laws. So far, the discrete element method has been applied in many industrial applications, and here are some of the examples: the continuous bender, contact screen, layering, and screw container. And the DM is actually not the only one method to simulate granular. We also have reactive molecular dynamics and classical molecular dynamics and the finite element method. And the DM sits in the middle between the molecular dynamic and finite element method, bridging the microscopic scale and the macroscopic scale. With the molecular dynamics, this method can capture atomic level interactions and is suitable for modeling chemical processes and bond dynamics. But in the DM, in the larger scale, this size is suitable for modeling powders, so that the DM can capture the particle level contact and is suitable for modeling powders. While the FEM, the finite element method, gives a higher or broader view about simulations, where it captures element level stress and deformation and is suitable for modeling the behavior of granular. Although this method is highly efficient for simulating large-scale systems, however, this method cannot be applied if the particle level detail is required. So, based on this scale, we need to understand the system size and the resolution we need before we selecting the appropriate method, and the DM stands out as an effective approach for simulations of granular flow in industries. Here are some of DM simulations conducted in such a way. And in many cases, we also couple with other methods such as computational fluid dynamics, volume of fluid to model the three-phase flow, the gas solid liquid flow, and here this diagram is the couple of discrete element model and the computational fluid dynamics. And if you are interested in our studies, you can visit our website. Although the DM appears as an ideal or established method, however, it remains some critical challenges exist for industrial applications. For example, in the simulations, the DM often use simple sphere to model particles, where the number is usually up to a few million. But in the actual industries, the particle shape are usually non-spherical, and the particle number can be immeasurable, which is almost impossible to be simulated by the standard DM. And this study will focus on these two challenges. Now I'm going to talk into the challenge. The first challenge is the particle shape. Why spheres are more common in DM? Basically, the sphere only needs one parameter to represent particle. It only needs radius, and that's all. So the sphere is more efficient to be simulated, and also the algorithm is more robust because the orientation of particle usually does not change the calculation of inertia of particle. So because of the efficiency and also the robustness, the sphere is more visible to be applied in large-scale simulations. But when we see the non-spherical particle, the computational efficiency is very high and prone to errors, making it challenging for large-scale simulations. So, in the existing studies, the particles with high sphericity and high mass are often assumed as when we see the SEM images of these particles, the particle shape are not perfect sphere, but they have some irregular features on the surface. So this kind of particle shape may lead to behavior different from perfect spheres. So that's why modeling particle shape is highly important in simulation. To model particle shape in DM, there are some methods that have been established, such as polyhedron, ellipsoids, super ellipsoids, super quadric, multisphere, and rolling friction. With the first type methods, like any types, any shape of particle can be approximated by using these methods. However, the computational cost typically increases when the representation of the particle shapes becomes more precise, which is often impractical for large-scale simulations. With the rolling friction, we resemble the bulk behavior of non-spherical particles, because the idea is the spherical particles tend to roll more easily than the non-spherical particles, and the rolling friction is introduced here to dissipate the rolling motion, similar to the non-spherical particles. Since the calculation is since the calculation is based on spherical particles, this method is especially feasible for large-scale simulations. In the previous studies, rolling friction has been applied to simulate the effects of non-sphericity, such as in the angle of repose test, landslide flow, and another angle of repose test. So the particle shape is actually like this, but in the simulation, they use spherical particles, but rolling friction is applied, and then they successfully simulate the work behavior of non-spherical particles with spherical particles. So the rolling friction is effective to approximate the macroscopic behavior of particles which has irregular features on the surface, and the energy dissipation becomes similar. And now I'm going to talk about the basic concept of rolling friction. So basically, rolling friction is a resistive torque that opposes the relative rolling motion. It reduces the rotational speed of a particle and eventually bring it to a stop when the friction is sufficient to bring the particle into the equilibrium condition. Without the rolling friction, the particle would continue to roll for indefinitely. So this is the equation of rotational motion in the end. Basically, this is the moment of inertia. This is the angular acceleration. This is the rolling torque, and rolling friction torque is introduced to this equation, where the direction always opposes the particles rolling. In references, actually there are so many types of rolling friction model, but I only bring two most common rolling friction models: the directional constant torque or DCT model, and the spring dashpot or SD type model. Yes, so this is the first model, the directional constant torque model. This model is named after constant because it applies a constant torque on a colliding particles regardless of the dynamics of the system. So this is the equation of the rolling friction torque. This is the rolling friction torque. This is the rolling friction coefficient. This is effective radius, normal force, and this rolling direction is to indicate to make sure that the rolling friction torque always opposes the rolling direction. So in this model, the magnitude of rolling friction torque is only dependent on the rolling friction coefficient. But when the normal force is constant, then the rolling friction torque becomes constant accordingly. And since this model is quite simple, the DCT model is considered as a standard rolling friction model, is widely used, and the free parameters is only the nu rho, the coefficient of rolling friction. However, when we conduct a simple case analysis where a particle is located on the flat surface and an initial velocity is assigned of 0.1 meter per second, and then this graph shows the rolling friction torque and the rolling distance over time. So, from the blue line, as we can see here, that the particle is initially rolls. The particle rolls away from its initial position, and then finally it comes to stop. Like the rolling distance becomes almost constant. But when we see the rolling friction torque, at first the torque becomes constant, but when the particles almost stop, oscillation, like permanent oscillation occurs. This is because when the rolling velocity becomes quite small, the rolling friction torque is the rolling friction torque overestimates the resistance needed to reach the equilibrium. That's why this kind of oscillation occurs. So the DCT model, although this model is quite simple, this model remains exhibits significant limitation regarding stability. So we need a more advanced model to introduce the rolling friction. The second model is the spring dashboard or SD type model. So different from the previous model that used only one equation, this model divides the rolling friction torque into two terms. The first term is called the adaptive torque because it depends on the relative rolling position and relative rolling velocity, and it has a maximum value when the value is similar to the DCT model. So, because of the adaptive rolling mechanism, the adaptive friction mechanism, this model is more stable than the previous one. Yes. However, this model has also limitations because it consists of three parameters: the K roll, eta roll, and mu roll. This three parameters is actually unwanted in simulations because when we want to set this kind of parameters, we need to calibrate with experiment. But if we have three independent parameters, it's difficult to determine which parameter should be changed to resemble the experimental observation. Jadi karena model ini menggunakan tiga parameter yang berbeda, ini akan sangat menyulitkan kalibrasi karena untuk menentukan koefisien-koefisien ini kita harus membandingkan dengan eksperimen, tapi parameter yang mana yang harus diubah itu akan sangat menyulitkan karena ada tiga. Kadang-kadang ya kombinasi antara ketiganya itu memang harus disesuaikan dengan eksperimen. And similar to the previous model, we also conduct simple case analysis, a particle with initial velocity of 0.1 meter per second. So at first the particle rolled away from the initial position and finally comes to stop. And when we check the rolling friction torque, the torque decreases as the rolling friction or the rolling velocity decreases, and finally the value of rolling friction torque almost zero by using this method. This is because of the adaptive rolling friction torque in these equations. So by incorporating the relative motion into the frictional response, this model can dissipate rotational motion more effectively. So basically, the ST-type model shows improved stability. So overall, the ST-type model is better than the density model. However, the parameters are hard to define. So there's still trade-off between stability and simplicity in the current rolling friction models. So this is the research gap. And now I'm going to go into challenge number 2, the particle number. In the discrete element method, because the evaluation is conducted at particle level, then the number of calculated particle is typically limited by the computational resources. So now, with the latest computer technology, 1 million particles is considered as a large number in EM simulations. Beyond 1 million, we often require high-performance computing techniques. However, this number is still far from that handled in actual industries. In the DM, when we involve 1 million of particles with a diameter of 100 micron size, it only equals to 0.00052 liters, or an eighth of a tablespoon. However, in the actual industries, the number of particles can be more than 1 million times larger than the simulation scale. So to address this huge gap, we need an innovative modeling strategy. And so to address the gap between the simulation scale and the industrial scale, our group has developed a post-grad model. So the general principle of the post-grad model is to represent a group of identical particles into one post-grain particle. And a post-grain ratio of L is used as a scale factor between the original and the post-grain particles. So as we can see here, the post-grain particle has a size three times larger than the original particles, and the number can be reduced significantly. And so, since the number of calculated particles is reduced, then the computational cost can also reduce accordingly. And this method is verified and validated in many cases, such as spouted bed, the gas solid flow systems, and the bed mill. And actually, we have more validation data. And as we can see here, that the macroscopic flow in the original system can be successfully represented by the post-grain model, although the number of particles becomes smaller. And when we check the calculation time, the post-grain model can significantly reduce the rotational time to reach the similar result, to gain results similar to the original particles. And this QR code links to the original paper of the post-grain model. So if you are interested, please visit the paper. And recent studies have shown the possibility of the combination, the possibility of combining the post-grain model and also the post-grain model and the rolling friction torque. So these four reports have shown the applicability of the rolling friction torque in the post-grain model. And they use the density model in the simulation. So this equation is the density model for post-grain particle, where all of the properties is assigned to the post-grain particle. However, as we discussed before, that the density model has significant limitation regarding stability. So we need to integrate the Program model with a more advanced rolling friction model. So to summarize the introduction part, in as an existing problem, the DM has been applied in industrial applications. However, the traditional DM faces significant challenges in real-world industrial application, especially in modeling particle shape and modeling a large number of particles, because these challenges often result in excessive computational cost. In the previous study, we found that the rolling friction is effective to present the effect of non-sphericity in particles. However, the primary challenge with the existing SD-type model is the calibration of multiple parameters. And to handle a large number of particles, we already have Program model. However, the existing approach relies on the density model, which has stability issues. So, the objective of this study is to develop a simplified and stable rolling friction model with a single parameter and integrated with Program model. And this study will be divided into two steps. First, we develop the rolling friction model based on the SD-type mechanism, and then we integrate it with Program model. The validation tests involve flighty rotating drum and a large-scale incinerator. The flighty rotating drum is selected because the non-spherical particles tend to have different pattern when they interact with the flight here. And so we would like to reveal the effect of non-spherical particles in this system. And then the second system is the industrial incinerator. So in this incinerator, a control plate is introduced here to prevent the particle from flowing to the outlet. However, when we conduct the experiment, we found that particle deposition observed on the control plate. However, this kind of phenomenon was not properly simulated using the existing model. So previously we had a simulation of incinerator. However, such kind of deposition was not properly simulated. So in this study, by using numerical simulation, we try to figure out the physics behind this kind of phenomenon. Now I'm going to go into the model description, starting off with the DM involving rolling friction, how we develop the rolling friction model, how we integrate the Program model with the rolling friction, and then brief introduction to the CFD for modeling the gas phase, and also how we model the wall boundaries. So this is the basic equation of DM. So basically the equation is based on the Newton's second law of motion. Here is the translational motion, and here is the mass and the acceleration, contact force divided into normal and tangential components. Here is the pressure gradient force, drag force, and the gravitational force. And here is the equation of rotational motion, where this term defines the rolling torque, and this term represents the rolling friction. So, and in the DM, the contact between particles is modeled as a couple of spring and dashboard. So this is for the normal component, this is for the tangential component, and to model the rolling to model the rolling movement, there's also a couple of spring and dashboard in the rolling mode. In the equation of contact force in the normal component is written like this, and this is the tangential component divided into two terms, and this is the equation of rolling friction torque based on the SD-type model. And this equation shows how we define the rolling component in the rotational motion. This study has two major contribution. First is the development of simple and stable rolling friction model based on the SD-type method, where the key improvement involves the requirement of only one parameter, the critical rolling angle, to model rolling friction, and where it offers better stability than the widely used DCT model. And second, we integrated the proposed model into the post-PDM and validated in plating drum, plating drum, and incinerator simulation, where we successfully demonstrated the macroscopic flow behavior in the original particles with the coarser particles. So this study further enhances the reliability of the coarser model, demonstrating its potential for optimizing a wide range of industrial applications. And it brings me to the end of my presentations. Thank you so much.
Baik, kita bahasa Indonesia aja. Kita masuk ke sesi tanya jawab ya.